everyone, welcome to the second problem solving session for the linear algebra. And our first question is, show that S1 is subset of S2 and S1 is linearly dependent, then S2 is linearly dependent. Now, S1 linearly dependent means that S1 linearly dependent means that there exists set S, let's say that V1 up to Vn, such that the C1 V1 plus Cn Vn equal to 0, and for some I from 1 up to n, Ci is not equal to 0. So not all Ci's are not equal to 0. So, but we know that this S is subset of S1, right? So, since S1 is subset of S2, so this set S1 is subset of S2. So, inside of S2, there exists S such that there is linear dependence between the elements of set S, and not all the Ci's are equal to 0. So S2 is linearly dependent. And this completes our first question. Okay, second question is, let's V be the polynomials over R, and our set S contains the vectors x minus 1, x squared plus 1, and x cubed minus x squared minus x plus 3. And the question is, determine if the subset S of the vector space V is linearly dependent or linearly independent. Now, to show the linear dependence or linear independence, we need to look at the is there any relation between them. Okay, let's look at the relation. Let's say C1 times x minus 1 plus C2 times x squared plus 1 plus C3 times x cubed minus x squared minus x plus 3 is equal to 0. Let's this equation satisfied. Now we need to look at whether the Ci's, C1, C2 and C3 are 0 or they are non-zero. If they are 0, then we need to say that this set is linearly independent. If one of them is not 0, we should say that it's linearly dependent. Now let's look at this one. Let's take x cubed common parenthesis. If we take x cubed common parenthesis, here we have x cubed. So we have x cubed times, we have only C3 plus x squared. We have one x squared here, and we have C2 times x squared, so we have C2. Then we have C3 times minus x squared, so we have minus C3 plus, let's say, x parenthesis. We have C1 here, we don't have x here, and we have minus x here, so C1 minus C3. And we have here, okay, it is gone, that is gone. Now we have the constant terms, plus, we will have the constant terms, we have minus C1, we have plus C2, and plus 3 C3 is equal to 0. Now, for every x, this should be 0. This is equal to 0 for every x. This is equal to 0 for every x in R. For every x in R. Since this is true for every x, every coefficient, like these are coefficients, right? These are our coefficients. Every coefficients must be 0. This should be 0, this should be 0, this should be 0, and this should be 0. So we have, from the first one, we have C3 is equal to 0. Here we have C2 minus C3 is equal to 0. Since C3 was 0, so C2 is equal to 0. So we have C1 minus C3 is equal to 0. And since C3 is equal to 0, C1 is equal to 0. So this one is also satisfied. If everyone is 0, this part becomes 0 again. So 0 equal to 0. There is nothing else in here. So here we have C1 is equal to C2 is equal to C3 is equal to 0. So we find that every coefficient will be equal to 0. So we can say that S is linearly independent. Third question is, let V be a vector space over field F and S a subset of V. Write the definition of S to span V. Then, using your definition, show that if V is equal to R square as a vector space over R and S is equal to the set 1, 3, 4, 3 and 2, 2, then S spans V. Okay, so we need to show that this one spans R square. So definition of this span is S spans V if for all V in V there exists S1 up to Sn in S, Sm in S, and C1 up to Cn in the fields such that B is equal to C1 S1 Cn Sn. So S spans V means that for every V in V we can express this V as a combination of the elements of S. Now in this question, our question, as a V we have R square, right? So take any elements inside of this V, R square, then V will be of the form A, comma B, and these A and B are in R. And we need to show that. Let's say 1, 3 is V1, 4, 3 is V2, 2, 2 is V3. We need to show that, or what we needed, V is equal to C1 V1 plus C2 V2 plus C3 V3, and C1, C2, C3 are in our field real numbers. Now this implies that V is equal to, V was A, comma B is equal to C1 times 1, 3 plus C2 times 4, 3 plus C3 times 2, 2. And this implies that in the first place we have C1 plus 4C2 plus 2C3. And in the second place we have 3C1, 3C2 plus 2C3. So we need to show that we can find such C1, C2, C3 so that C1 plus 4C2 plus 2C3 is equal to A, and 3C1 plus 3C2 and plus 2C3 is equal to B. So let's write this here. Okay. Now we have C1 plus 4C2 plus 2C3 is equal to A, and 3C1 plus 3C2 plus 2C3 is equal to B. Now we need to find such C1, C2, C3. Now let's say C3 is equal to 0. Let's take C3 is equal to 0. Now, if C3 is equal to 0, then we will have C1 plus 4C2 is equal to A, and 3C1 plus 3C2 is equal to B. So let's multiply this one by minus 3. So then we will have 3C1 minus 12C2 is equal to minus 3A, and 3C1 plus 3C2 is equal to B. So if we add these to each other, then we will have minus 4C2 is equal to minus 9C2 is equal to 3A plus B. So this implies that C2 is equal to minus 3A plus B over minus 9. So this implies that 3A minus B over 9. C2 is equal to this one. And if the C2 is equal to this one, then we will have, let's put this one here, 3C1 plus 3 times 3A minus B over 9 is equal to B. So this implies that 3C1 is equal to, this cancels, we have 3. 3B minus 3A plus B over 3. I take this one here. So I will have C1 is equal to 2B minus 3A over 9. Sorry, 4B minus 3A over 9. So this one and C2, C3 equal to 0, and this is equal to C2. This is a solution. Now we need to check our answers. We need to check this one. So A is equal to A was C1 plus C1 is 4B minus 3A over 9 plus 4C2 4 times 3A minus B over 9 times 2C3, C3, which is equal to 0, and this cancels. So we will have here 4B here, we have minus 4B here, they are cancels. So this cancels this one. So we have minus 3A plus 12A, so we have 9A over 9 is equal to A. So this is correct. Let's look at B also. B is equal to 3 C1. 3 times 4B minus 3A over 9 plus 3 times C2, 3A minus B over 9 plus 2 times 0. Now, this cancels each other, we have 3, and this cancels this one, we have 3. So we have here 4B, we have here minus B, so we have 3B here, and we have minus 3A here, we have plus 3 here. These two cancel, so we have 3B over 3 is equal to B. So this is also correct. So this is the solution. So we can express every AB as, we can express for every AB in R, AB is equal to C1 times 1, 3 plus C2 times 4, 3 plus C3 times 2, 2. As C1, C2, C3 we define below. As, C1, C2, C3 are like below, above. So S spans W. Now, but I find this one as C1, C2, C3, but this C1, C2, C3 are not unique. You can find other answers, other solutions. Such that if we take, for example, C1 is equal to 0, if we take C1 is equal to 0, then C2 will be A minus B, and C3 will be minus 3A over 2 plus 2B. Or now also we can say C2 is equal to 0, then we will have C1 as B minus A over 2 and C3 as 3A minus B over 4. Or there is other answers. For example, if we take C1 is equal to B over 2 and C2 is equal to A and C3 is equal to A over 3 minus B over 4. So there are infinitely many solutions for this C1, C2, C3. And this was the midterm 1 question. Question of this year, question 2. Now, question 4 is, show that V is equal to F to the N over the field F. The set S is equal to the 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, and goes to 1, 1, 1, 1 at the end place is a basis. Now, to show some set is basis, for first you need to show that S is linearly dependent, and second thing we need to show that S spans F. Now first thing we will show that S is linearly independent, not dependent, linearly independent. So to show this one, I need to look at this equation. Let's look at C1 times 1, 0, 0, 0, plus C2 times, there is 1 at first two components and the 0 other ones. Goes like this, plus dot 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 Cn times 1 1 1 is equal to 0. Now we need to show that these Ci's are equal to 0. We need to show that Ci is equal to 0 for every I from 1 up to n. Now let's look at this one. So we will have C1 in the first component. Then we will have C2 plus, sorry, this is wrong. So at the first component we have C1, C2, we will have C3 till Cn, right? So at the first component we will have C1 plus, C2 plus, C3 plus Cn. At the second one, now in this case we don't have the C1, so we will start with C2 till Cn. So we will start with C2 till Cn. It will go like this, and at the last one we will only have Cn. And this is equal to 0 0 0. This is actually 0 0 0. So this implies that C1, C2, C3 up to Cn is equal to 0, right? And then C2 plus Cn is equal to 0. So this goes like this. Then we will have Cn minus 1 plus Cn is equal to 0, and then we will have Cn is equal to 0. Now, since Cn is equal to 0, we will have that Cn minus 1 is equal to 0. Then, after one step, we will find Cn2 is equal to 0. And if we go here like this, in this step we will find C2 is equal to 0, and in this step we will find, if we go from bottom to top, we will find C1 is equal to 0. So Ci is equal to 0 for every I from 1 up to n. Therefore, S is linearly independent. Now we need to show that S spans V, F. To show that S spans V, now we need to show that S spans F. So every element of F, Fn, let's take V in from F to the N. So V will be of form x1, x2, xn, such that xi's are in F for every I. Now we need to show that V is equal to C1 1 0 0 plus C2 1 1 0 0 plus Cn 1 1 1. Now we need to find such Ci's. So x1 up to xn is equal to C1 plus C2 plus Cn, C2 plus C3 plus Cn, and this goes like this till the Cn. So from here we have that x1 is equal to C1 up to Cn, x2 C2 up to Cn, and xn is equal to Cn, and x minus 1 is equal to Cn minus 1. So from here we can choose Cn as xn. Then from here, since Cn is equal to xn, this gives us Cn minus 1 is equal to xn minus 1, right? We are putting xn here and we are taking Cn minus 1 in this side and sending this one to this one. For example, let's look at the xn minus 2. And then we will have Cn minus 1. Sorry, why it's minus? Sorry, it's plus. This one is plus. So we will have, if Cn is xn, then we will have Cn minus 1 is equal to minus xn plus xn minus 1. Right? Yes. Then we will have xn minus 2 Cn plus Cn minus 2. This is equal to this one. And this is equal to xn minus xn plus xn minus 1 plus Cn minus 2. So xn's are cancelled. So we will have Cn minus 2 is equal to minus xn minus 1 plus xn minus 2. And if you go like this, you will find that C2 is equal to minus x3 plus x2, and C1 is equal to minus x2 plus x1. So we find Cn's like that. So we will have, let's look at now let's look at the x1. Let's check. Whether these ones are satisfied. Let's say Cn is equal to minus, let's say Ci is equal to minus Cxi plus 1 plus xi for every I from 1 up to n minus 1, and Cn is equal to xi. Let's check. X1 is equal to C1 plus Cn, right? So this is equal to, now what we said, Ci is equal to minus xi plus 1 plus xi. So C1 is equal to minus x2 plus x1, then C2 is equal to minus x3 plus x2, x3 is minus x4 plus x3, and it goes like this till xn is equal to plus x2. Then now here we have minus x2, we have plus x2, they cancels. Then we have minus x3, then we have plus x3 here, that it cancels. Now we have x4, we will have x4 here, so they are cancels. So also we will have minus xn here. Here we have minus xn plus xn minus 1. So they are cancels. Also we will find this one, and this is equal to x1. So this is true for x1. Let's check for any I. So if we take xi for any I, then this sum will start from ci plus 1 till cn, right? Here, if we take the second one, if we take the x2, we will have this one, for example, c2 to cn. If we take c3, it will be c3 till cn. So we will have ci to cn, then this is equal to it's not equal to n, then this one will be ci is minus xi plus 1 plus xi minus xi plus 2 plus xi plus 1, and it goes like that till xn, and again they all cancels, and this will also cancel, so we will have xi. This is also true, and xn is equal to cn, which is xn. This is just true. So v is equal to x2 minus x2 plus x1 times 1, 0, 0 plus minus x3 plus x2 times 1, 1, 0, 0. It goes like this times xn times 1, 1, 1. So this implies that S spans f to the n. So since S spans f to the n, and before we check that S is linearly independent, so S is a basis for f to the n. S is linearly independent and S spans f to the n, so S is a basis for f to the n, and this completes the question. Question 5 is find the basis for the subspace of the polynomials degree at most 4 over R generated by polynomials 1 minus x minus 2x cubed plus 1 plus x cubed plus 1 plus 4x cubed and x squared. Now, let's look at the subspace generated by these ones. Now, first we need to look at that whether there is an dependence or not, like whether this set is independent or not. Now, so let's say this, but let's look at this one. Let's say 1 minus x minus 2x cubed plus 1 plus x plus 4x cubed is equal to 2 plus 2x cubed, and this is equal to 2 times 1 plus x cubed, right? So 1 plus x cubed is equal to 1 over 2 times this one plus this one. So we can discard 1 plus x cubed. So we discard this one. Let's look at whether there another dependence relation. So this is okay, right? There is nothing in between, and there is nothing in between these two. So I think they are independent, but we still need to prove that. So let's look at that c1 plus 1 minus x minus 2x cubed plus c2 times 1 plus x plus 4x cubed plus c3 times x squared is equal to 0. Let's look at whether this one gives us C1, C2, C3 is equal to 0. Now we will have, as a constant term, we have C1 plus C2. C1 plus C2, this one is constant term. Let's take x parentheses. We have minus C1 here. We have plus C2 here. There is nothing here. Let's look at the x squared term. There is no term with x squared here. There is no term with x squared here. There is only this one. So we have x squared times C3. And we have x3 times, we have minus 2c1. And we have 4c2 is equal to 0. So from here, but there is no constant term here. So constant term must be 0. And there is no term with x, so this one should be 0. And there is no term with x squared, this one should be 0. And there is no term with x squared, so this term must be 0. So we have c1 plus c2 is equal to 0. Minus c1 plus c2 is equal to 0. From these two. So if we add these to each other, we will have c1 like cancels each other. So we have 2c2 is equal to 0. This implies that c2 is equal to 0. So c1 plus c2 is equal to 0. So c1 is equal to 0. And from here we have c3 is equal to 0. So minus 2 times 0 plus 4 times 0 is equal to 0. So this also satisfies. So c1 is equal to c2 is equal to c3 is equal to 0. So they are independent. 1 minus x minus 2x cubed, 1 plus x plus 4x cubed, x squared are linearly independent. So basis. So this will generate the space. So this will be generate the space since 1 plus x cubed is equal to 1 over 2 times this one plus this one. So since also they are also linearly independent, this is the basis. 1 minus x minus x squared, 1 plus x plus 4x cubed, and x squared is the basis. So this completes the question. In the question 6, our field is the field with 3 elements, F3, and our vector space is F to the 4, built as a vector space over F, and let S is equal to 1, 0, 2, 1, 2, 0, 2, 1, 1, 1, 2, 1, and 0, 1, 0, 0. And let B span S, find the subset S, which is a basis of W, and calculate the dimension of W. Now first we need to find basis, we need to find linearly independent set, right? Let's look at here. Let's look at this term. 1, 0, 2, 1 plus 2, 0, 2, 1. Now, since we are at the field with 3 elements, 1 plus 2 is equal to 0. So we have 0 in the first component. 0 plus 0 is 0. 2 plus 2. Sorry, this should be 1. This should be 2. Okay, 1, 2. So 2 plus 1 is again 0 and 1 plus 2 is again 0. So there is a relation between this one and this one. So we can discard this one. So discard 2, 0, 1, 2. So we omit this vector. Now let's look at the other ones. Okay. So let's look at 2 times this one. Two times 1, 0, 2, 1 plus, then we have 2 plus 1, 1, 2, 1, right? And this is equal to 2 plus 2, 0, 0 plus 1, 1, 2 times 2 is 4, 4 plus 2 is 6, and 6 is equal to 0, and 2 times 1 is 2, plus 1 is 0. So this is equal to this vector, right? So again, we can discard, or we can omit 0, 1, 0, 0. Now we have only 2 vectors, right? Now we have this one, let's say S prime, and we have also 1, 1, 2, 1. We can find the other 2 from these 2. Now we show that these 2 are linearly dependent. Since we can say this one, okay, I want to say last thing. Now, W is span S, right? Since we can find this term and this term from these 2 terms, W is equal to span of S prime. Since 0, 1, 0, 0 is equal to 2 times 1, 0, 2, 1 plus 1, 1, 2, 1, and 2, 0, 1, 2 is equal to minus 1, 0, 2, 1. Now we also need to show the linear dependence. Independence. Now, whether they are linearly independent or not. Now we look at C1 times 1, 0, 2, 1 plus C2 times 1, 1, 2, 1 is equal to 0, 0, 0. So we have, in the first component, we have C1 plus C2. In the second component, we have only C2. There is C1 times 0 here. In the third component, we have 2C1 plus 2C2. And in the last one, we have C1 plus C2 is equal to 0, 0, 0, 0. From here, at second component, we have C2 here, we have 0 here, so we have C2 is equal to 0. But we have also C1 plus C2 is equal to 0, so since C2 is equal to 0, C1 is also 0. So C1 and C2 is equal to 0, so S prime is linearly independent. So basis is equal to 1, 0, 2, 1, comma 1, 1, 2, 1 is a basis for W. So this completes the question. And in this question, we also need to find the dimension of W. Since the basis contains two elements, dimension of W is equal to sine of this beta, which is equal to 2. Okay. Question 7 is determine whether the followings are linear transformation or not. So let me first give you the definition of the linear transformation. A linear transformation from V to W, V and W are the vector spaces of the same field, is a function t from V to W with the following properties. T of V plus V1 plus V2 is equal to TV1 plus TV2. T of C times V is equal to C times TV with for all V1, V2, V1, V2 in V and for every C in the field. Okay. Part A is let U be a subspace of vector space B and let the TS from V to V quotient U as sending every V inside of V in the V plus U. Now we need to show that this is a linear transformation or not. Now let's look at the, take any V1, V2 in V and let's look at the T V1 plus V2. This is equal to V1 plus V2 plus U. And as a definition of addition in the quotient spaces, we know that this is equal to V1 plus U plus V2 plus U. So this is equal to TV1 plus TV2. Also take any, first one, it's okay, let's look at the second one. Take any V in V and C in F. Let's look at this one. C times V is equal to, T of C times V is equal to CV plus U. And again, as an product over the quotient spaces, we know that this is equal to C times V plus U. So this is equal to C times TV. So therefore, T is an linear transformation. In part B, our vector space is C square and our field is complex numbers and our map defined by the formula sending the tuples ZV's to the tuples Z conjugate and W conjugate. Now we need to show that this is a transformation, linear transformation or not. Now let's take, it's not a transformation. Let's look at Y. Let's take 1, 0 inside C square, okay? And TZW, T1, 0 is equal to 1 conjugate, 0 conjugate, which is 1, 0, okay? Now let's look at the I times 1, 0. I in the fields. I in the fields. Now this is equal to Ti 0 and this is equal to I conjugate 0. So which is minus I 0. And look at the I times T of 1, 0. So this is equal to I times 1, 0, which is equal to I 0. And minus I and the I, they are not equal. So these two are not equal. So therefore, since I times t1 0 not equal to t of I times 1 0. So t is not a linear transformation. Now part C is the operation from the polynomial degree at most 4 to polynomial degree at most 4 as t of f is equal to x times f second derivative minus 2x times first derivative of f plus f. Let's take any f and g in P4 R. And let's look at the f plus g. Let's look at the first derivative of f plus g, which is derivative of f plus derivative of g. These are the rules of the derivation. So let's look at the second derivative of f plus g, which is equal to first derivative of f plus g. Derivative of this one is equal to second derivative of f plus second derivative of g. So t of f plus g is equal to x times second derivative of f plus second derivative of g plus minus 2x times first derivative of f plus first derivative of g plus f plus g. So this is equal to x times f prime, f second derivative, minus 2x times first x times first derivative of f plus f. We have this one and this one. So also we have x times second derivative of g minus 2x times first derivative of g plus g. So this is tf and this is tg. So first thing is okay. Now we need to show the second property. Let's take C in R and F in P4 of R. Then first derivative of C times F is C times first derivative of F, and second derivative of this one is equal to C times second derivative of F. Then T times CF is equal to x times second derivative of this one is C times second derivative of F minus 2x times first derivative of C times F prime and plus F C times F. If we take C outside, we will have x times second derivative of F minus 2x times first derivative of F plus C times F, and this equals C times T of F. So second part also satisfied. So T is a linear transformation. And thank you for listening to me. See you next time.